Welcome to Cambridge IGCSE Physics, Lesson 18.1, Internal Energy. Today we explore how temperature changes affect the total energy of particles in matter. This is a core topic, essential for understanding thermal physics and energy transfer processes. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know that rise in temperature increases internal energy. This means understanding the direct relationship between thermal energy and particle motion. Understand internal energy is total energy of particles. This encompasses all forms of energy within a substance. Relate to kinetic and potential energy of particles, connecting microscopic particle behavior to macroscopic thermal properties. These objectives align with Assessment Objective 1, focusing on knowledge and understanding of fundamental physics concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. Internal energy means the total kinetic and potential energy of all particles within a substance. This includes both their motion and their positions relative to each other. Temperature rise means an increase in the average kinetic energy of particles. When particles move faster on average, temperature increases. Particle energy means the energy possessed by individual atoms or molecules. This can be kinetic energy from motion or potential energy from intermolecular forces. Understanding these terms precisely is crucial for mastering thermal physics concepts. Let's explore our first core concept. What is internal energy? The fundamental principle states that internal energy is the sum of all particle energies within a substance. This means every single atom or molecule contributes to the total. The definition is internal energy equals total kinetic energy plus total potential energy of all particles in a substance. Mathematically, we express this as U equals EK plus EP, where U represents internal energy, measured in joules, EK represents the total kinetic energy from particle motion, and EP represents the total potential energy from particle interactions. The diagram illustrates particles in a container with different speeds. Notice how faster particles, shown in red, have higher kinetic energy, while slower particles, shown in blue, have lower kinetic energy. This principle is fundamental because it connects microscopic particle behavior to macroscopic thermal properties we can measure. Now we examine the relationship between temperature and internal energy. The key relationship is higher temperature means higher internal energy. Here's how this works. When temperature increases, particles move faster on average. This is the fundamental definition of temperature in kinetic theory. As kinetic energy increases with particle speed, following the relationship, kinetic energy equals half mass times velocity squared. Therefore, internal energy increases because it's the total energy of all particles. The diagram shows this clearly. On the left, we see low temperature with particles moving slowly, shown by short blue arrows. On the right, high temperature shows particles moving much faster, indicated by longer red arrows. The green arrow represents heat energy being added. Notice how the particle speeds increase dramatically. Remember, temperature measures average kinetic energy per particle, while internal energy measures total energy of all particles combined. Let's work through our first example. The problem states, a gas is heated and its temperature rises from 20 degrees Celsius to 80 degrees Celsius. Explain what happens to the internal energy. We are given initial temperature of 20 degrees Celsius and final temperature of 80 degrees Celsius. We need to explain the internal energy change. Step 1. Identify the change. Temperature increases by 60 degrees Celsius, which is a significant rise. Step 2. Apply the principle. Higher temperature means faster particle motion. This is the fundamental relationship in kinetic theory. Step 3. Consider kinetic energy. Average kinetic energy per particle increases because particles are moving faster. Step 4. Determine internal energy change. Total energy of all particles increases because each particle has more kinetic energy. The answer is internal energy increases because particles move faster, and internal energy is the sum of all particle energies. Example 2 applies the same principle to different states of matter. The problem is, compare internal energy of ice and steam at the same mass. The data shows ice at 0 degrees Celsius and steam at 100 degrees Celsius, both with equal masses. Now we analyse systematically. First, compare temperatures. Steam is much hotter than ice, 100 degrees difference. Second, consider particle motion. Steam particles move much faster than ice particles because temperature measures average kinetic energy. Third, evaluate kinetic energy. Steam has higher kinetic energy per particle due to faster motion. Fourth, determine internal energy. Steam has greater total energy because it has the same number of particles but each moves faster. The diagram shows this clearly. Ice particles, blue, are relatively stationary in a rigid structure, while steam particles, red, move rapidly in all directions, shown by the arrows. Mathematical skills are crucial in thermal physics. Let's examine 3 key skills. First, energy units. The SI unit for energy is the joule, symbol J. For large energies, we use kilojoules, symbol kJ, where 1 kilojoule equals 1000 joules. Always include units in calculations. Second, temperature conversion. To convert Celsius to Kelvin, add 273 to the Celsius temperature. For example, 25 degrees Celsius equals 25 plus 273, which equals 298 Kelvin. Kelvin is the SI base unit for temperature. Third, proportional relationships. For ideal gases, internal energy is proportional to absolute temperature. This means if you double the temperature in Kelvin, you double the internal energy. These relationships are fundamental in thermal calculations. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, what happens to internal energy when temperature increases? This tests your understanding of the fundamental relationship. Question 2 is intermediate. It states, explain why hot coffee has more internal energy than cold coffee. This requires you to apply particle theory to a real situation. Question 3 is advanced. The question is, a gas doubles its temperature from 300 Kelvin to 600 Kelvin. How does internal energy change? This tests your understanding of proportional relationships. For all questions, remember to show your reasoning clearly. Use scientific vocabulary, like kinetic energy and particle motion, and explain what happens at the particle level. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how internal energy concepts apply in practice. In heating systems, radiators transfer thermal energy to air, increasing the internal energy of air particles, which makes them move faster and feel warmer to us. In cooking, heat from stoves increases the internal energy of food particles, providing energy for chemical reactions that change texture, flavour, and digestibility. In engines, fuel combustion rapidly increases the internal energy of gases, causing expansion that drives pistons and generates mechanical power. These applications show why understanding internal energy matters. Career-wise, this knowledge leads to many professions. Thermal engineering designs, efficient heating and cooling systems, energy systems, engineering optimizes power generation, and material science studies how internal energy affects material properties. The concepts you learn today become tomorrow's innovations in sustainable energy and efficient technology. Let's review the solutions. For question 1, the answer is, internal energy increases because particles move faster, increasing total kinetic energy. This is correct because internal energy is the sum of all particle energies, and higher temperature means faster particle motion. For question 2, we explain, hot coffee particles move faster than cold coffee particles, so total particle energy is higher. This demonstrates understanding that temperature differences reflect particle motion differences. For question 3, internal energy doubles because it's proportional to absolute temperature. When temperature doubles in Kelvin, internal energy doubles too. Now, exam success tips. First, always explain using particles. Mention particle motion and energy in your answers. Second, use correct vocabulary. Say internal energy, kinetic energy, and temperature precisely. Third, give complete answers. State what happens and explain why it happens using particle theory. Fourth, check units. Energy should be in joules, temperature in Kelvin or Celsius as specified. Let's summarize today's lesson. The key points to remember are: First, internal energy is the total kinetic plus potential energy of all particles in a substance. This fundamental definition connects microscopic particle behavior to macroscopic thermal properties we can measure and feel. Second, the temperature relationship shows that higher temperature increases internal energy. This happens because temperature measures average particle kinetic energy, so hotter substances have faster moving particles. Third, the particle model explains that faster particles mean more kinetic energy. This microscopic view helps us understand why heating increases internal energy. These three concepts form the foundation for understanding thermal physics. For further study, review particle theory and energy concepts regularly. Practice explaining thermal processes using particle motion and energy changes. The next lesson covers specific heat capacity, which builds on today's work by examining how much energy is needed to change temperature. Ensure you understand internal energy before moving forward, as thermal physics concepts build systematically.